Welcome back to another explainer. I am absolutely thrilled to guide you through today's topic because honestly, we're looking at something that feels pretty close to magic. We are talking about fluid mechanics. Now, I know, that might sound like a dry textbook physics topic, but I promise you it is anything but. This is the invisible force driving our daily lives. It's a hidden superpower that literally makes the modern world function. Okay, let's dive into this. I want you to think about a truly wild, everyday impossibility. How does a tiny, basically effortless push of your foot on a pedal manage to bring a massive 2-ton vehicle moving at highway speeds to a completely dead stop? I mean, if you were just using your own physical strength, no way. It would be impossible. So how exactly do we solve this mystery? Well, the answer to our mystery is fluid mechanics. It's the study of the physical laws governing liquids and gases. And mastering these laws allows us to do some seriously incredible things, like multiplying our force and defying gravity. This is the secret superpower behind so much of the modern technology we rely on every single day, not to mention the natural world around us.
So here is our roadmap for this explainer. We're going to start with the magic of fluids, move into Pascal's principle, see that in action with everyday hydraulic systems, then switch gears to Archimedes and buoyant force, and wrap it all up with the science of floating. By the end of this explainer, you're going to have a solid mastery of these core concepts. All right, part 1, the magic of fluids under pressure.
To really grasp the magic here, we first need to talk about pressure, which is simply how much force is applied over a specific spread out area. Because you see, fluids behave very differently than solids do in confined spaces. If you push on a solid block of wood, the whole block just moves forward, right? But imagine you have a sealed plastic bag completely filled with water. If you press down on one side of that bag with your hand, the pressure doesn't just stay right under your fingers. Instead, the water shifts and the bag bulges out in completely different spots. The force you applied actually traveled right through the water. Moving on to part 2, Pascal's principle, multiplying force. So the crucial point is how we define this fascinating behavior scientifically. We use Pascal's principle. It states that pressure applied to a confined, incompressible fluid is transmitted equally in all directions throughout the fluid. Now, incompressible just means the fluid can't be squished down into a smaller space, kind of like water. And because it can't compress, the pressure doesn't just sit where you pushed. It travels absolutely everywhere inside that closed system without losing a single ounce of its strength. Let's walk through a mental thought experiment to see why this is so powerful. Picture 2 syringes connected by a plastic tube completely filled with water, no air bubbles at all. Syringe A is really small, and syringe B is much larger. According to Pascal's principle, if we push the small syringe plunger, that pressure transmits perfectly through the water in the tubing. But because the second syringe has a much larger surface area, that exact same pressure applies force across that entire wider area. In physics, force equals pressure multiplied by area. So if the area goes up, the force goes up proportionally. The end result? The larger syringe plunger moves with a multiplied, massive force. A tiny push magically creates a huge push. Which brings us to part 3, everyday hydraulic systems, Pascal in action. And this brilliantly illustrates how we take something like plastic bags and syringes and use it to literally shape our world. Just think about where we use this trapped fluid mechanism. Car brake systems use a fluid to multiply the tiny force of your foot into the massive force needed to clamp the brakes. Hydraulic car lifts in mechanic shops, they use this to lift entire vehicles with a simple pump. It's how those dentist chairs smoothly raise and lower you. It's used in massive industrial hydraulic presses. It is even the exact same physics at play when you squeeze the bottom of a toothpaste tube, and the pressure transmits through the paste to push it out the top. The whole shebang runs on Pascal's principle. Let's shift gears for part 4, Archimedes and buoyant force, the weight of water. Now this brings us to a rather legendary historical discovery. The story goes that the ancient Greek mathematician Archimedes was tasked with figuring out if a king's crown was pure gold, but he couldn't damage the crown to find out. He was completely stuck. But while stepping into a bath, he watched the water level rise and spill over the edges. He suddenly realized that the volume of water pushed aside, or displaced, could actually be used to measure the volume of an oddly shaped object, which would solve his puzzle. He was apparently so excited he jumped out of the tub and ran completely naked through the streets of Syracuse shouting, "Eureka, I have found it!" That naked realization led to a foundational law. Archimedes' principle states that the upward buoyant force exerted on a body in a fluid is exactly equal to the weight of the fluid that the body displaces. I really want to highlight the elegance of this. The missing weight you feel when an object is submerged in water matches exactly the weight of the water that the object physically pushed out of the way. Breaking that down even further, we get buoyant force. This is the upward push of a fluid against an object, which counteracts gravity. Think about being in a swimming pool. Have you ever noticed how much easier it is to lift a heavy rock or even carry a person when you're standing in the water with them? It's not that your muscles suddenly got way stronger. It's that the water is actively pushing up on the rock alongside you, basically giving you a hand to lift it. Finally, part 5, the science of floating, shape, mass, and volume. Let's move to and see how this builds. If water pushes up on everything, why do massive steel cargo ships float so easily while a tiny little pebble sinks straight to the bottom? Well, it all comes down to volume, density, and shape. Sinking objects have a small volume, high mass, and a solid, compact shape, which makes them highly dense. They just don't push enough water out of the way to generate a strong upward force. Floating objects, on the other hand, are designed with a large volume and a wide, hollow shape. This forces them to displace a massive amount of water. And since buoyant force equals the weight of the displaced water, displacing more water means a much stronger upward push. That is exactly how thousands of tons of steel can float. Let's challenge ourselves with a quick thought experiment. Imagine we have aluminum foil in two forms: a tightly crumpled foil ball that sinks because it's compact and displaces very little water. But take that exact same amount of foil with the exact same mass and shape it into a flat little boat. It floats. Its wide shape displaces far more volume, which increases the buoyancy. Meanwhile, a solid rubber ball will sink because of its high density and low volume. It all comes right back to our guy, Archimedes. We have covered some incredible ground today, from the force-multiplying magic of Pascal to the displaced waters of Archimedes. So I want to leave you with this final provocative thought. Look around your room right now. Think about the vehicles parked outside, the plumbing hidden inside your walls, the goods that were literally shipped across oceans just to get to you. What hidden fluid mechanics are making your modern life possible right this very second?